So, hey everybody, I'd love to introduce Mark Taylor from Sandia National Labs, who is going to talk about the computational challenges of, well, modeling the climate of the whole damn world. Welcome, Mark.
Yes, I'll talk about our work developing a cloud resolving model and targeting these exascale computers. I have a lot of contributions from, I've listed some key contributors, but in most of my slides, I've tried to put references when necessary. But I've surely forgotten some people, and apologies for that. But it's a big team effort. A quick outline, I just have a few slides on an overview of our project that funds this work called E3SM, Exascale Energy Earth System Model. Most of my time I'll spend talking about SCREAM. That's our new atmosphere model, stands for Simple Cloud Resolving E3SM Atmosphere Model. We are targeting cloud resolving resolutions, which makes it especially expensive. And our goal is to run on these new exascale computers that the Department of Energy is building. It's one of our main missions. I talked mostly about porting SCREAM to these exascale systems and show some performance results. And then I just had a comment on machine learning and GCRMs and digital twins at the end. So E3SM is about 50 FTEs spread over 100 staff and 8 different DOE laboratories and several universities, contractors. Classic Earth system model with atmosphere, land, ocean, and ice components. We have a science mission that comes from DOE, looking at energy and water issues out 40 years, and our key computational goal, which is my involvement, or my main work, is to ensure E3SM will run well on these upcoming exascale computers. Our project is on GitHub. Most climate models these days are open source, meaning that release the code for the releases. We're one of the first to go to what we call open development, meaning the whole thing is on GitHub, all the PRs and everything is done publicly. And we have a reasonable website, e3sm.org. A timeline of the E3SM project is starting around the 1990s, actually, with the rise of parallel computers. That's how DOE got into, started working with the community Earth system model. It was called something different at that time, but with NCAR. So for quite a while, over 10 years, the DOE labs worked with NCAR through about 2015 on the CESM. And I think probably many in the audience are familiar with CESM. 2015, DOE reorganized all their modeling development projects into this one larger project, E3SM. Motivation by really focusing model developments on particular science questions from DOE Office of Science, and to ensure the model will run well on these exascale computers. And we started with CESM version 1.2, since many in the Energy Lab system had been working on that model for a long time. Our first release, so our V0 is CESM version 1.2. 2018 was our first release, already diverged somewhat from CESM. In particular, we adopted the spectral element dynamical core in the atmosphere, and the MPAS components for ocean and ice. And then our V2 release was in 2021, and our V3 releases should be next year. Just to go through the components briefly, we follow the CESM coupling structure, so they have now 5 components, all running in a single executable, but each individually talking through the flux coupler, which maps the fluxes and state variables between the different models and controls the execution. So I already mentioned MPAS models for sea ice, land ice, and ocean, the ELM land model, and most of my talk will be on the EAME-XX atmosphere model. EAME refers to the Fortran code, EAME-XX, the rewriting it in C++. I probably don't need to show this video, but I will anyway. This is from our V1 release. I like to show this just for people not in the climate modeling field to convey that the climate models really look like weather forecast models. And I think people outside our field have a more intuitive understanding of a weather forecast model. So this is just showing that was ocean currents. And then it slows down, the video slows down quite a bit to show the atmosphere on top of the ocean. So the ocean currents are still moving in this video, just much slower than the atmosphere. And this is a kind of the bare minimum in the atmosphere resolution to get tropical cyclones. And you can see some tropical cyclones, and they make a nice, cool, they stir up the ocean and leave a cold wake, a streak of yellow, stirring up the surface layer of the ocean behind them in their tracks. So E3SM, I like to tell people, think of it as a weather forecast model, but we don't bother with complicated initial conditions or 3-day forecast, but we have to run that for tens, if not hundreds of years in individual simulations. It makes it quite expensive and is then typically run at lower resolutions than a forecast model. So jumping into the atmosphere component, and this is true of all modern global atmosphere models for many years now. It may start to change in the future, but hasn't quite yet, at least in kind of production models. It's divided into two components: the dynamical core, core, solves the equations of motion. We're using the non-hydrostatic equations with the shallow atmosphere approximation. And then in addition to that, linear transport of about 40 species. In the cloud resolving model I'm talking about, we have 10 species because we have we're using prescribed aerosols. We don't have to transport aerosol species. And the dynamical core contains all the MPI communication, and then all the scalability issues come from the dynamical core. And then that's coupled to an extensive suite of subgrid physical parameterizations for all the unresolved effects, precipitation, radiative heating, phase change, things like that, often referred to as column physics because the individual columns, and I don't know if my cursor shows up, probably not, but there's an orange column here indicating the column physics. The columns don't talk to each other.
Yeah, and we can see your mouse.
Okay. Oh, very good. So the dynamical core is what sets your grid and your numerical methods. Until recently, most global atmosphere models were all based on traditional latitude-longitude grids, either finite difference, finite volume, or spherical harmonics. But most modeling centers starting in the 2000s have been transitioning into unstructured grids. That's to get rid of this. The lat-long grid has this pole problem. All the resolution really clusters there, just creates some mostly problems for parallel computers. And so we're in E3SM, we're using the spectral element method, and that's a finite element method that requires quadrilateral elements. So the cube sphere grid shown here is a natural choice for us, which is what we're using. It's an inscribed cube, and it's further subdivided into quads.
Actually, question.
Yeah.
Is that choice based because you want to use GPUs and similarly like structured architecture, why you want cubes?
So originally the choice was made for spectral elements was when going to these unstructured grids, there's a lot of numerical challenges, getting good accuracy when you move away, when you're on a less structured grid. And spectral element method preserves, it's one of the few methods that's explicit, unlike most finite element methods, and preserves its order of accuracy even in these unstructured meshes. Finite volume methods often lose order of accuracy on these types of methods. Since that time, I mean, this was developed in parallel. There's been a lot of good finite element methods, especially on these, really the dual grid of the icosahedral grid. So the TRISC scheme in particular that addresses many of those issues as well. So it was really, that was our motivation. But then we were fortunate in that the spectral element method is this, everything is this tensor product structured calculation, unlike the finite element approaches, which happen to map very well on GPUs. So I'd say that wasn't a, I'd like to say it was an intentional choice, but it was more of a
Got it.
lucky coincidence.
Right.
Or maybe you could say that since we were targeting GPUs, we stuck with the spectral element approach as opposed to
Abandon it, yeah.
switching to something else.
Very nice.
Yep, thank you. And then just to, so once you go unstructured, then you have this ability to do regionally refined meshes or local refinement. And that's been quite popular in the last couple of years. It's really been a useful capability where you can statically refine over a region of interest. No production or operational models I know of use adaptive refinement yet. That's still a challenge, but I know it works very well in other applications, but for this application, that's still a challenge. But static refinement has been very useful. Okay, so then just a slide showing resolution where the typical E3SM simulations run. This is a slide showing topography over California, centered over the Bay Area, with a 200-kilometer resolution here, so relatively large squares, 25 kilometers, 1 kilometer. Most E3SM simulations and IPCC class climate change assessment simulations are still run at 100 kilometers, somewhere in between here, although there's a few at 50 and 25 kilometers. And at cloud resolving, we're really targeting 1 kilometer, which is shown here. But all the work I'm going to show that's still quite expensive is at 3.25 kilometers. And I'm going to refer to that as cloud resolving if you can get to this resolution in your global atmosphere model, although many people might object that, and some people will call that cloud permitting or storm resolving resolution. This figure, interestingly enough, was taken from the Green Flash project back in 2009. That was the project to run a cloud resolving model, to build a dedicated machine to run a cloud resolving model at 1 kilometer. And they were going to use ARM-based chips. So an interesting project, but I don't think they ever got the funding to actually build the massive machine that would have been needed.
And when you say it's cloud resolving, you mean that you don't need a subscale model, the regular atmospheric differential equations, just near clouds. Okay.
Yeah. And I'm not going to, so from my point of view, so I'm sort of simplistically saying get to 3 kilometers, we're going to call it a cloud resolving model, but you're right. There's a very good scientific motivation to get to these scales. And it's exactly what you're saying is removing the convective parameterization. So I do have one, I at least mention that bullet in this slide. So cloud resolving simulations with, here it says grid spacing less than 3 kilometers, although we're at 3.25 kilometers. Really 1 kilometer, but 3 kilometers you're getting close and you can start turning off this convective parameterization. So that's the cloud resolving refers to, not resolving individual clouds, but resolving the overturning circulations responsible for cloud formation. And at lower resolutions, they have to be parameterized, and it's commonly blamed as one of the largest sources of uncertainty in climate models and climate projections. So it's a big push to get to cloud resolving models to remove this parameterization. You still have a host of others, and you can run, of course, regional cloud resolving models and short global cloud resolving models right now. So we know they do work well. Resolved convection does substantially reduce major systematic errors in precipitation because of its explicit treatment of convective storms. And so then we believe it will, I have here, improve our ability to assess regional impacts of climate change. This was just an animation from a again over California, of an atmospheric river in our 3.25 kilometer cloud resolving model. Oops. So Scream, that's our cloud resolving model. This is just a high level overview of the components in it. The dynamical core, the resolved scale fluid dynamics is a spectral element method that I mentioned briefly. For radiation, we use a C++ port of the RTMGP package. Microphysics is a P3 scheme, and then aerosols are prescribed in at least our initial versions of the model. And then a parameterizing action, we don't have that parameterization. And that's these two are responsible for the simple in Scream. It's simpler because it doesn't have prescribed aerosol, no convection. And running these resolutions has a lot of benefits. The one I like is it's really striking how real the simulations look, and you can now compare simulations directly to satellite observations. So this in the middle is a Scream simulation, plotting shortwave cloud forcing, and then zoomed in directly compared to satellite images. This is a diamond simulation, so that's a cloud resolving intercomparison model project that provides initial conditions. So we run this initial, it's from January 22nd, 2020. You can run this initial condition and compare with observations at least for a couple of days, which is what we're doing here. This is after 2 days. And then just one more example of something cloud resolving models do a good job at. On the climate side, it's the diurnal cycle of precipitation. So this is not not how much rain you get, but when do you get most of the rain. This is difficult to get in models with parameterized convection. Difficult to get it right in cloud resolving models, but they do a better job at these kind of statistics. Okay, now I'm going to switch to exascale computing. And returning back to this resolution, just some numbers here. Our 100-kilometer traditional simulations, they run at the atmosphere component runs at 64 simulated years per day on 85 CPU nodes. But our cloud resolving simulation is 1 simulated year, so 60 times slower. It requires 32,000 GPUs just to achieve that rate. So these global cloud resolving models are incredibly expensive, and they're typically run on the world's largest computers. And in the US, those are these new exascale machines. The Department of Energy has been leading the US effort to develop the first exascale machines. And that's shown on this roadmap here. And this is up at the top is related to E3SM development. So this is kind of the machines we have access to and the machines we're targeting, and the exascale machines, especially for Scream. So the first exascale system to be delivered was Frontier just early this year. And the next one will be Aurora at Argonne, and Frontier's at Oak Ridge later this year or early next year. Sorry, I'm going to close that pop-up window. And then within our lab system, the other machine we run on is called Perlmutter. And here, just a description of these machines and what they have. But the key point, for our point of view, is they're all GPU-based. That wasn't clear when the project started, that the US exascale machines would be GPU-based, but basically all the horsepower in these machines, something like 98%, comes from GPUs. So our exascale strategy has been evolved into running the model on GPUs. And really within DOE, that's the only cycles that will be available in the near future.
So, question on this. I'm thinking of some of the older architectures, like what the cell processors back in the day of what the Roadrunner and the Blue Gene, which are a bunch of dumb processors, but a lot of them, GPUs are a very specific kind of architecture. So why is it really where the industry is going uniformly because this is just what everybody's doing, or are there if you had to make a new processor just for climate or something, or some more focused numerical workloads, is GPU your preferred architecture, or would you want a better, more focused thing?
So I would say it's not our preferred architecture. If we could build a machine for climate, it probably wouldn't be GPUs. So it's a little bit of it, the exascale machines that mean running an exaflop on the Linpack benchmark, but they support many different applications. So in some sense, they're building these machines to get to an exaflop, and some applications run great, other applications run pretty well. Climate, I think we get a slight benefit over CPUs, but not like factors of 10. I have some data on that later on. So they are good, but it's a lot of work to port your code to running on them.
So then what's for climate, what do you need? Like, would it be more like a CPU, more of a flexible architecture, or more of a constraint, but different constraints architecture?
Yeah, you mean if we could build our own machine and design our own chip?
Exactly, yeah.
Yeah, so the best results, so GPUs actually can outperform them, but for very little work, we get really excellent results on modern like EPICs and these new Intel Cascade Lake CPUs. If I had even more control, you could, for climate, drop the cache coherency on those chips. So build a chip like that and get rid of all that circuitry devoted to cache coherency, because we run MPI and don't need the shared memory protection that you need for that. And so that would either lower the power or let you put more floating point units on it. That's just only mildly informed speculation, though. I don't know that you could build such a.
Oh yeah, no, just like what there is actually a good answer for this. And Michael, you had a question.
Yes, my question is following on your question. So I see that you have like 2 CPUs there, 6 GPUs per node. Do you run something on both CPUs and GPUs at the same time? And if so, what is the desirable mix?
Yeah, so our initial target, and we're not at this state, we're running atmosphere only simulations right now, or atmosphere land. But we leave the land on the CPU because it's it's like less than 2% of the total cost. And even the ocean, it kind of depends on the resolution, but a very good use case will be cloud resolving atmosphere, eddy resolving ocean. So the cloud resolving atmosphere runs completely on the GPUs, and it only needs a few CPU cores to manage that, launch the kernels. And then the rest of the CPU cores, we will run the ocean model, our traditional Fortran version if we want. But we're also eventually porting the ocean model to GPUs as well. So yes, that's a good, these mixed architectures are useful for us for that reason. It's very problem dependent. If you want to run high res ocean driven by a low res atmosphere, then you need the ocean on the GPU, of course. You can imagine all the different scenarios.
Okay.
So our strategy to run on GPUs has been, we basically spent a lot of time trying to get Fortran with OpenACC and even a little work on OpenMP to work, and it was mostly just frustration. And we switched to a C++ strategy. We decided to rewrite the code in C++, and then we use for the execution model library, Kokkos or YAC. I'll say a little bit about that just to hide the different GPU or CPU execution statements. So we write. And this has been a very robust and well-supported solution. It lets us get on the machines very early. The vendors always had good C++ support, and Fortran is very lagging. I think the Fortran support will eventually catch up. So I don't think it's a bad choice to go with Fortran, to stick with Fortran and wait for OpenACC. OpenACC is getting there on NVIDIA, but has a long way to go on AMD GPUs. And OpenMP, in our experience, still very immature. So that's we went with the C++ approach due to frustration with Fortran maturity and vendor support mostly. But yeah, almost all codes are atmosphere and climate models and weather prediction models are still written in Fortran. That's starting to change. I have a slide. I tried to summarize the other approaches being taken. And one of them is domain-specific languages. And I'll say a little bit more. We just didn't have familiar staff that was experienced with those and didn't want to write our own and went with C++. One slide on this Kokkos library. It's a C++ library which provides an abstraction layer around the code related to on-node parallelism, so loops and arrays. So we have Kokkos arrays and then a parallel for execution that will then run that for loop on CPUs, GPUs, and various GPUs. And the Kokkos is very well supported. Right now, it's used by a lot of different applications within DOE at least. And we've quickly been able to get on new GPUs. I'll have results from NVIDIA and AMD, and we have early results from Intel hardware. The downside of C++ is the code is definitely a lot more complicated as compared to the Fortran. So objectively, the domain scientists have a legitimate issue with working with the code. It may drive us to a model which is certainly what we're doing initially, where computer scientists, work with domain scientists to write the code. The domain scientists write the algorithms and even maybe test them in Fortran, and then the computer scientists port them. But we hope that long term our scientists will be able to work directly in the C++ code. Another advantage of rewriting a model from scratch is that we remove, in some cases, decades of code that's been accumulated in these models for a long time. The last statement is most of the complexity you see in this particular example, and I'm not going to go into details, is due to the use of what we call packs. That was we put that in order to vectorize properly on CPUs. So C++, I don't quite understand well why, but C++ codes generally do not vectorize very well automatically compared to Fortran. That's a strong suit of Fortran, generating AVX vector type instructions. And to get competitive performance on CPUs, we need to put this in. If you want to, be 20, 30% slower or 50% slower on CPUs, go after only GPU performance, you can skip that part. And then just to mention, in addition to Kokkos, we use another library called YACL in the radiation package. This is a smaller, kind of simplified version of Kokkos, but interesting because it's targeted at Fortran code, so it supports Fortran-like arrays, and it makes it makes it simpler if you're just porting a Fortran code to not have to because the end result is minimal changes to your arrays. It still looks very much in Fortran style. And then just to mention other efforts of getting cloud resolving models running on GPUs. I have a probably incomplete summary here. And NECAM I put because they're the most well-known and the world's first global cloud. They've been running global cloud resolving simulations for over a decade. They're actually, I don't know if they're considering GPUs, but they're traditionally a Fortran code, and they're running on this large CPU-based near exascale machine in Japan, Fugaku. So in some sense, that if they pursue that path, they don't have to port to GPUs. And Max Planck in Europe, the ICON model, they're going with a Fortran OpenACC approach. They have very good results on NVIDIA GPUs. Europe is getting a big AMD machine, so it'll be interesting to see how long it takes to get good results on that, different vendor with a less open ACC support, but it's starting to be there. And then the Allen Institute and working with GFDL has a model called PACE. That's a DSL, so it's all written in Python, and then converted into so Python is the DSL and converted into a GPU and CPU code. It's GT4Pi package. UKMO, their upcoming Alfric model uses Cyclone. That's their in-house DSL. It's a unique in that it's a Fortran. You write in it's a DSL that you write in Fortran, and then it converts it into GPU code. And then the Klima project, very interesting because they're using Julia. That's a language designed for writing mathematical expressions. I really like Julia as a language, so it'd be great to see results there. Write it in Julia. Julia provides very sophisticated information about the dependencies, and then you can create a GPU backend out of that. Okay.
So question on all this, what makes, I mean, all these things are, if I were going to dumb it down, is a bunch of parallel arrays that have backends for whatever runtimes that then map to the underlying hardware.
Yeah.
And so then what makes a programming model good? Because I'm also thinking like Google would be like JAX or NumPy or a few of these for Python. But is it like that? These are Fortran-like multidimensional with slicing, or is it you want bigger objects that are not just numbers, or maybe not irregular computations?
I think if you stick to that approach, which is just parallel 4, then they're all reasonable, and it will come down to maturity because different approaches have different levels of maturity. But I think that model they should all eventually work equally well. The one thing we do with Kokkos that's often not supported in other models is hierarchical parallelism. So we don't do just parallel 4s. If you do just parallel 4s, you have to push all your loops into every subroutine so that the loop in the subroutine contains the loop over all columns and all grid points and things like that. So we do, which Kokkos supports and GPU support, you launch teams of threads at high level, all with a set of grid points. And then you go into your subroutines and you still have 128 threads left to parallelize the loops inside the subroutine over the vertical, in our case, 128 vertical levels. So that's, to me, the only minor difference between them is if you want to go down the hierarchical parallelism route.
And one thing you did not mention is load balancing, job scheduling, like dynamic static, any of that stuff. Is that relevant?
We do that in our traditional model. We have inherited from CESM. So CESM has a nice night-day for the physics, night-day load balancing. That's the extent that we do, where you, because the daytime has the radiation, which is very expensive. So we like each processor to have half their columns in daytime and half the columns in nighttime. So not geographically located, but we don't do anything sophisticated in the dynamics. And it's worthwhile to do that communication to scramble the data to get that night-day balance. At Cloud Resolving, we're not doing that. So we do have some load imbalance in the physics in the current Scream implementation.
Got it. Yeah, thank you.
This is just, some people asked us how long it took. So this is a slide on that. I don't know if it's that interesting, but we did develop the Fortran and the C++ code simultaneously because the C++ code took a while before it was usable for doing anything. So Fortran code to develop, to play around the physics configuration and develop the non-hydrostatic dynamical core. And while we were doing that, the C++ code, we spent 2 years working with what I call prototyping. We really, the team learning what's going to work and what's not going to work. And then after that, it basically took us a year to port so here we're just porting Fortran code at this point, a year to port the non-hydrostatic model, a year to port the physics, another year for the glue code that hooks them all together. And then just in 2023, we got the whole model running on this Frontier system. And we have a nice paper I can send. People are interested on the, we were fortunate, and then we got the model running right when the Gordon Bell introduced this climate prize. So we were able to submit to that. Climate's not well represented in the general Gordon Bell, you know, fastest performance on the real application, because we don't use these machines as efficiently as other applications, but there's this new category for the next 10 years just for climate models.
Well, a question on the chat. What's the size of this team in this effort?
So E3SM as a whole, not the atmosphere team, is 50 FTEs, about 100 people. This effort is probably the core people doing this work. I'd say it's 3 FTEs, maybe split over 5 people.
Got it. Thank you.
Yeah. In the DOE, we have this problem that people are often on multiple projects, and we have very few people 100% on one project, but they'll be on closely related projects. So it's, you know, I know if you had a dedicated team, I think it would go faster. Okay, so performance data. First, I'm going to start with just the dynamical core, where we looked at very detailed single node performance. And it's probably not detailed performance of Y, but detailed comparison of different CPUs and different GPUs on a single node. It's hard always to compare GPUs and CPUs, so I just like to point this out. A GPU node usually contains, in our case, 4 to 6 GPUs and a CPU. So a GPU node, right, is, in terms of TDP, about 4 to 8 times more power than a CPU node. They also cost a lot more than a CPU node. It's hard to get those numbers. Hard to get the numbers that HPC centers actually pay for these GPU nodes, but I think it's also at least 4 times more expensive. The power, that's TDP, right? The actual power. GPUs appear to be more efficient when running our codes. They're usually not running the TDP. So it's hard to get this number also, but the power consumption might be closer to 3x. A GPU node is 3x. So when I compare CPUs and GPUs, it's just difficult to do a truly fair comparison by power or by cost. So I'm mostly going to compare GPU nodes versus CPU nodes. But to start with, because we have data going back about 10 years now, I'm going to compare a single GPU to a single dual socket CPU just for the dynamical core. And that's this data here. I like this data just because it shows the trends over time. So this is performance of various GPUs and various CPUs going all the way back to 2012. So this is kind of a mini app we use to benchmark performance. So it's our dynamical core, although it's our hydrostatic dynamical core, not our non-hydrostatic, in a certain configuration. And the lowest curve on here is the Ivy Bridge, one of the Intel Xeon from 2012. And this is kind of a normalized performance. Higher is better. And the CPUs and GPUs are, getting better in this metric every year. They are using, the newer CPUs and the newer GPUs use a lot more power than the Ivy Bridge CPU. Our best results here at the top, the green is actually a CPU. That's so dual socket AMD EPYC node, 128 cores, and then this number here is a A100 NVIDIA A100 GPU. The x-axis is the work, so it's sort of like scalability. It's the number of, in our case, spectral elements, but you can think of it as grid points being assigned the GPU or the CPU node. So there's a dependency. Your GPUs do best when there's a lot of work or a lot of grid points because they have so many more lightweight cores. But so from what we can tell, CPUs and GPUs are both continuing to get better. To go back to your question originally about, is GPUs the future? I wish I knew if CPUs were going to stagnate and GPUs were going to keep getting faster, or vice versa. And then just a comment, we have this pink line here. This is the A64X FX node that's in Fugaku. That looks quite slow, but most of these are 400 to 600, 700 watts. That one is like 200 watts. So this particular metric is rather unfair to that chip. And those nodes actually only have one A64 FX, where all the other CPU nodes have two. Okay, so turning to the full model, and this is now so that was DICOR. This is DICOR in physics.
Actually, before you get to that, the last thing was actually very interesting, because that means you can put many more of those cores of those nodes inside the same building for the same power.
Yeah.
So, but is that right? Or at the MPI level, you run out of parallelism and doesn't make a difference?
So in a traditional model, we definitely run out of parallelism, but in a cloud resolving model, you won't run out of parallelism. So it's actually and that was the idea behind this green destiny. I had this slide from this project from 2009, millions of low powered chips. It hasn't, I think that's still an idea at this stage. It hasn't been proven. The results from Fugaku, I haven't seen actually really good results from Fugaku yet.
Thank
but
you.
I think it's a good, I think it's a viable approach.
Cool. And Michael, you had a question?
Yes. So what about the top level parallel loop, shall we say? Is it synchronous like in old style MPI, or it's asynchronous?
Is this referring to the hierarchical parallelism example?
To the overall, basically to the benchmarks that you're showing.
Yeah. Oh, right. So the highest level loop here would be over the spectral elements.
Mm-hmm.
In the spectral element, and this is a property of finite element methods that's nice. Every spectral element, the calculations are all completely independent. So that loop has no, it's perfectly, the loop over elements is perfectly parallelizable. And then once they've completed all their calculations, mm-hmm. then there's this mass matrix inverse step that involves all the communication.
What about between the nodes?
So this benchmark is single node, but it is using MPI. We usually benchmark both. Sometimes we even have both curves. MPI between the cores. It's always single node or single GPU. So GPU no MPI, but the CPU results are MPI or threads, whichever is fastest.
I guess my question is that MPI traditionally run in synchronous mode, but it also allows asynchronous execution. So do you use synchronous lockstep or asynchronous?
I don't know. So what I do know, we don't do a lot there. We do, a few standard things, like we post all our receives ahead of time, try and do some work when possible, post receives, try and do as much work as possible, and then do the weights on the.
So it's asynchronous essentially. Okay, thank you.
But we don't get. I don't believe we get much asynchronous work done because usually you still spend most of your time waiting. There's not a lot of work we can do while the messages are in flight. And I don't even know if modern MPIs can make progress asynchronously. But yeah, sorry, I don't know much. Don't really know that.
Okay, thanks.
Sorry, I'm just. So this next one is low res, not the cloud resolving model, but this is just to show. So here we run low res, sort of the point that was made before. Now we run out of parallelism at this resolution. So we're running the 100-kilometer model up to about, so we start to run out of parallelism around 100 nodes. And so this just shows first our Fortran. So this is our performance portability slide. And the first thing I'll show is the C++ versus Fortran. So this is this here is the bottom curve is a black and blue. This is not a very good CPU, the IBM P9, comparing Fortran and C++, so they're basically identical on this curve. One of our rather slow CPU, just an old CPU, but it's still around in this machine, Summit. And then the next curves here, black and blue, are on a EPYC. So this is one of our fastest CPUs we have access to, dual socket, 64 cores per socket EPYC. And here's the C++ code in blue, slightly faster than the Fortran code. And that's probably because Fortran, we rely on the compiler to do all the vectorization. In the C++, we've tediously hand-forced vectorization in every loop possible. And then the red are the GPU results. And there's 3 different GPUs demonstrating a little bit of performance variability because we're getting good results on both NVIDIA, which use CUDA behind the scenes, and AMD GPUs, which use HIP underneath the hood to run. And the fastest one is the A100, the circles here. And so this is, again, a node-to-node comparison. So it doesn't, GPUs are, there's a regime where a GPU node is significantly faster than a CPU node. And 4 to 10 times faster in this regime. If you say GPU nodes consume 3 to 4 times more power, we are looking at a better performance per watt. And then this is data on, that was comparing Fortran and different GPUs. Here now we're only running our Fortran code on 2 big machines, the 3 machines, Perlmutter, Summit, and Frontier. It's too many curves here because each benchmark has 3 numbers: the die core, which contains all the MPI communication, the atmosphere model, and then the full model, because we still have to spend a lot of time talking to the other components that are running on the CPU. So I don't want to go, I have a simple one next, but I just wanted to show here we get the same benefit as the Perlmutter CPU node. So this is AMD EPYX, which is our fastest CPU system we have access to. And then the GPU nodes, both 4 MI250s or 6 V100s, give you a nice speed up over a CPU node. And then just extracting some curves out of that. I'll focus not on I'll start with just the atmosphere. So that's, the piece we really focused on running on the GPUs at cloud. This is now cloud resolving resolution. This is our configuration we use for these diamond model intercomparisons and for our longer simulations. And this is scaling. The thin line is perfect scaling. So we get decent scaling. It does start to roll off on 8,000 nodes. It's 32,000 GPUs. So there is we were talking about limits previously. Go to 1 kilometer, then you're looking at, basically unlimited 300,000. You could probably scale to hundreds of thousands of nodes. And then we make a big deal. This is kind of a psychological benchmark or threshold to exceed 1 year per day for a cloud resolving model, which our atmosphere is running at 1 year per day. Unfortunately, the full model, the coupling to these data components providing surface conditions, got us down to below 1 year a day for the full model. So this is Frontier. So this is our first runs on an Exascale computer and getting to 1 year per day. All right, this is my last slide. This is just a comment on the machine learning. I'm actually not involved in any machine learning work, but I think it's very exciting and a lot of interest in the community. And it's somehow all tied to global cloud resolving models and this popular digital twin concept. So I think, it's a lot of work to have or interest around having a digital twin of the Earth. And I think the global cloud resolving model, they have the realism to serve that role, but they're so expensive. I think a digital twin needs to be much more affordable to explore that. And there's a lot of approaches. I think there's no slam dunks right now. No, we don't know what's going to, where the big successes are. But just to mention, this work training machine learning models on purely observations, so you wouldn't even need a model to basically replace models based just on observations. Train a machine learning model to replace the GCRM. The approach I like is to train a machine learning model to do bias correction. So you have a low-res model and then a high-res model, and you machine learn the difference so that you can bias correct the low-res model. And then a lot of work, still a lot of uncertainty in these parameterizations, so a lot of work. Can you get better parameterizations through machine learning? And I'll stop here. Thanks.
Yeah, well, thank you very much. Are there any questions on the call? Okay, so I'm just, first, Michael.
Thank you. So I do have a question, more philosophical one. So you had this choice either to keep the source code in Fortran and spend your effort to maybe push the Fortran vendors to support all the fancy new architectures, or like follow the bulletin and port the original code to something that already has support.
Yep.
So could you tell more about this choice that you made, and you apparently gave up on pushing the vendors?
Right. It's our key computational mission is to run on these machines, and we really wanted to run, the day they were turned on, we wanted to be up and running. Mm-hmm. And we really felt C++ was the only way to get to that level of readiness on these architectures. And we have to support too AMD and Intel, the Intel GPUs later on this year. And the Intel GPUs do not support OpenACC. So OpenACC wasn't, you would have to have OpenMP working if you're going to run on Intel GPUs. So for us, it's a key part of our mission, and we wanted to be ready right away. It's to me, the main motivation. I think some people say Fortran is dying. I don't believe that. I think Fortran and OpenACC or OpenMP will eventually be mature enough for these codes. Another argument, I don't know if this is true, but another argument made is it's much easier to hire C++ programmers than Fortran programmers. I don't generally think, I think people interested in this application and HPC don't really care too much about the language. But yeah, professional software engineers, definitely C++ is easier than Fortran hiring.
Yeah, well, if I were to write some high performance, I would not choose C++, of course. It's just such a curse.
Yeah.
So domain-specific language is what you were saying. So having Fortran as that domain-specific language would be, of course, desirable.
Yeah. For our application, it's such a nice language. I agree.
And so so one thing you haven't, I'd like to hear more about is adaptivity. So to what extent is it useful or challenging to use adaptive meshes? And also there's a flip side of adaptively load balancing and using the hardware given the changing now conditions in the algorithm.
Yeah, there's a lot of good research on that in the community, and I'm not that, so the comment I'll make is it hasn't made it into the kind of production models. Adaptivity is challenging because Convection is the main thing you would want to adapt to resolve, instead of doing cloud resolving, resolve convection, resolve the cells where you're going to get convection. But you often need high resolution to know if you're going to have convection. So you need to, the work I've seen, you do a little pre-refinement to see if you need to refine more. So it just becomes challenging to do that. But I think it's a good, a good area to pursue. And then I think the hard part about kind of adaptive domain decomposition is that the time steps are so, I forget the numbers, but it's milliseconds per time step. There's just so little work, especially because we're always scaled out for each time step for the communication, that to move things around is going to swamp all any potential gains. Even on the GPUs, right? If you leave a little bit of code on the CPU, it just ruins all your performance. We can copy back and forth at the time step level to couple with the other components, but we can't afford to copy back and forth. The entire time step has to be resident on the GPU. We can't afford a single copy in that time step.
Yeah, that makes a lot of sense. Thank you. And then you talked about machine learning and that kind of stuff, but maybe more computationally, a lot of the stuff, the wider workflow within which the stuff works has to be like you to do uncertainty quantification, run the thing many times. It's horribly expensive. You may even to create a data set for training data set for a machine learning model. You have to run it many times to pick the right parameters for a lot of these. I don't care what the ML algorithm is. You have to run it a lot of times. So how does that data-driven or many samples kind of workflow fit into the very expensive simulations we're talking about?
Yeah, no, good question. I don't want to. I'm not even going to venture a guess. I just don't know. I think that's a key challenge. We're the only thing I can say is the cloud resolving modeling on these new machines will be that much easier and that much faster, and we can afford that much more simulation than we could before. So
that makes sense. So then let me ask a flip side. Is it how feasible or useful is it to do regional models on, I'm not going to say real or fake Earths? Because you have a small thing on whatever scenarios, you can actually have a very diverse training set of what physics looks like for any of these models or parameterizations.
So I think you can do a lot of training. You can certainly do a lot of training at cloud resolving resolution with regional models, or in our case, we're trying to replace regional models with refinement. So you can run cloud resolving over a region of interest inside a global model. And that makes it much more, so you're not getting cloud resolving everywhere, but you can do a lot of process studies with that, understand what cloud resolving models are doing right and improve them, or understand processes at a more fundamental level that will inform parameterizations for other models or things like that, or train a machine learned model region by region and then put it in the global model. I'm just speculating there, though.
It makes a lot of sense. Yeah. That's really good. Yeah. Thank you very much. It was fantastic. Yeah. Thank you for coming. Have a great day.
All right. Thank you. Thanks for your attention. Bye.
Bye. Thanks.